Hi everyone, my name is Mohammed Sidki. I'm the AIA Mateo County Chapter President. I want to welcome you all to our June ARE study session covering project planning and design and project development and documentation. Before we start, I would like to make a couple chapter announcements. First, we want to say thank you to our sponsors. Our ARE series sponsor, Heather Young Architects, and our gold chapter sponsors, Romic Engineers, MN Builders, and our silver chapter sponsors, Da Vinci Marble and BKJ Structural Engineers. Session rules. So please mute yourself if you are not talking to reduce background noise. Feel free to unmute and ask questions at any time. Also, feel free to add questions to the chat bar below. Do not discuss any specific exam questions as not permitted by NCARB, and note that the session is being recorded. Guest speaker. So today guest speaker is Pardees Azodanloo. She's a job captain at DES Architects and Engineers. Pardees got her master's in architecture from the University of Minnesota before moving to the Bay Area and joining DES in early 2019. She's passionate about getting her architecture license, sharing her knowledge, and encouraging others to pass their exams. Pardees passed PCM, PJM, and CE. Now she's studying PA, PPD, and PDD all together, as there are so many overlapping topics. So I'll stop sharing my screen right now, and Pardees, you can start sharing yours.
Okay, everybody, you can see my screen?
Yes, we see your display.
Okay, thank you, Mohammed, for the introduction. So as he mentioned, I'm still in the process of like right in between my exams. Pardees Azodanloo, studying for my AREs. I just a disclaimer that I'm not a mechanical engineer. I'm not a professional in any of that. I'm just sharing my study process notes. I failed the PA and PPD once so far, so I know what a hard process it is to go through these exams. There are so many books, so many videos. So I'm just, I think at least for mechanical system, I came to a good conclusion, or just some study notes for myself to review, and I'm just sharing that. If you guys, please don't take these as the solid answer for anything. And if you guys found an error, please feel free to let me know. And like we can inform everybody who's participated in the meeting that this has been, this needs to be revised. And then if you have any questions in the middle of this, please feel free to raise your hand, unmute, as Mohammed mentioned, but I might not be able to answer. But I'll try to find an answer eventually, and we'll follow up through an email. And that. So today we're going to go over psychometric charts, principles of refrigeration, and then different HVAC systems and components. Honestly, failing PA and PPD ones, I think it's really just good to have some general information about everything. We really don't need to get in depth. I think I've made that mistake so far myself, that sometimes I get in too much into like structural systems or heavy calculations, but we need to really understand what it is and what chart tells us in order to understand the concept. So we might not daily use psychometric charts, but it's good to understand what it is. It's basically gives you information about wet bulb temperature, which kind of it's a mixture of the dry bulb temperature and the humidity ratio. And something to note is that this ratio on the humidity level, it's coming from here all the way to the top. So all these 20%, 40%, 60%, it's all the percentage in here, all right? At this last portion gets to 100% of ratio. So if you just Google psychometric charts, you see different versions. Some of them have numbers. So one thing that we might get in exams and I've seen sample questions of not from NCAR, from other sources, is just they give you a specific dry bulb temperature and a humidity ratio, and they want you to figure out the wet bulb. So it's basically just reading a chart. So it's good to know how to do that. And generally, a psychometric chart presents a physical and thermal properties of how much moist or wet the air is. And anybody, by any chance, I'm sure a lot of people, Jorge, is more experienced than me, but do you know what this diagonal angles in this chart represents? There will be some yellow boxes throughout this presentation, and I will delete them eventually. It's just things that you guys might know, and I'd just like anybody to participate. It's good too.
So feel free just to unmute yourself.
Yeah.
Give the answer. It's better really to give a wrong answer here rather than in the exam. So just just whatever you think.
Dew point?
Correct answer.
Is it a dew point?
It's you're close. Dew point is kind of like when I think dew point is when there's like 100% humidity in the air. So the air cannot handle more than that. But it's the enthalpy. And I don't think we necessarily need to know the concept in depth, but it's just good to know. It might come in the options of a question. It's a total heat in the air, not necessarily the total humidity in the air, which is calculated by BTU. But you were close, thanks for that. So anybody knows where or why we would use psychometric chart in general? Like why would you use psychometric chart?
To find comfort zone.
Exactly. So depending on the temperature that we need, or with the zone that we are in, our building is, and according to how much humidity we have, or what the temperature is during the year, we need to figure out what type of system we need for our building. So do we need all the time we need to heat the building, all the time we need to cool the building, or where are we at? So basically we want to get our temperature, our indoor temperature, into a comfort zone, which is here, which is a ratio of specific temperature for the dry bulb to the humidity level. So so like here, when you have when you don't have like the humidity is low in percentage and you're a relatively hot area, this is evaporative cooling. That's what we do. And generally wanting to know, and we're going to get to it when we talk about evaporation process and as a refrigeration method, we would figure out, because like the only times you can use evaporation or evaporative systems is when you don't have too much of humidity, because just even thinking about it, when you want to get the cooling process from when the wind gets through something wet, you need to have enough room of humidity in the temperature, because humidity is basically like a lot of moist in the air, and you need to have enough room for that moist to happen to cool it off and use that evaporation. So anybody can use what would we use if we are low in temperature, and meaning it's cold, and it's low in humidity. This is where would this fall into? So this would be just conventional heating, because you just need the system to be heated. You're very low in temperature. You just need to get the system or your building basically hotted. And here, anybody wants to guess this one? It's you're high in humidity, but obviously it's hot in temperature, so it's around 90 in hundreds.
Conventional cooling.
Conventional.
Exactly,
Yeah.
exactly. So you need your AC and conventional cooling. So it's just good to know where. I don't think we're gonna be asked to fill in the blanks here, but just conceptually understand where each of these fall. It's really good. This slide, I think it's from, it's from the book NEEB. And here is actually a sample question. So while looking at that chart, one of these, any of them, I'll put that here just for reference. Anybody can answer this. Somebody wants to volunteer and answer this question. I'll read it up and anybody wants to know the answer. So at 100% relative humidity, wet bulb temperature is greater than dry bulb temperature. Wet bulb temperature is less than dry bulb temperature. Wet bulb temperature is equal to dry bulb temperature, or the relationship of wet bulb and dry bulb temperature can only be determined using the psychometric chart.
At 100%.
Maybe I'll zoom into this one with all these numbers. Anybody?
Maybe greater.
Let's zoom back on this one. That these lines are kind of distracting. So the 20 here. So we have to know. Okay, let's go back to this one. These diagonal lines is distracting a little bit, I think. So if you look at how, so here, this last line here, it's the 100% humidity, right?
Mm-hmm.
So any point, any temperature of this wet bulb here, and you drag it down to the dry bulb, what would it be? It's the same, right?
Yeah.
So it's actually equal.
Mm.
Does that make sense? And I zoomed in on this one just because if you Google, there are too many options of dry bulb or what is it, psychometric charts. But because I wanted to show how this one had the percentage on top of it, and I wanted to show you that the percentage, these lines go all the way up to here. But actually, these lines are kind of distracting because this 50, we have to drag it all the way down to look at the dry bulb temperature. This line is the dry bulb temperature, and this line is the wet bulb. So we have to ignore these blue and green ones at this point when we're talking about 100%, because 100% is this last line of humidity ratio. Okay, in case anybody is interested to know, to look at MEB is a book literally this much thickness. So it's not a book you're gonna read like cover to cover. This link here, Wily Chart has, it's free. You can, over the chapters, there are, each chapter has, I think, either 12 or 10 or 11 questions. So I think they're good questions just to know the concepts. And if you don't know the concept, you can look into the chapter. Probably All the Firms is one of those books that probably all the firms should have one. If I don't think it's something you want to buy yourself, but I just put the link for your reference, and then obviously I'll share the slide.
I did rent that book from Amazon again because I don't think you need to buy it. I think it was like for like $30 for 6 months, and you don't need it for more than that time.
Yeah.
Before we move forward, if you are not getting what Pardees is explaining, feel free to ask questions. Just say, hey, I'm not getting this concept, or I'm not getting what is the wet versus the dry, or any other concepts. Like feel free to ask questions.
No questions? We're moving to the next chapter. So if there are any questions on the psychometric chart.
If you can just go back to slide number 5. One of the things I actually remember, and it's been a while, like for example, the evaporative cooling, you get a project scenario where it says a project in Florida, for example. So you need to recognize that Florida is hot, but it's humid. So for example, when you have, let's say, 3-4 choices, you are not going to use evaporative cooling. That's not one of it. But if the project was, let's say, in Arizona, in Tucson, Arizona, that's when evaporative cooling would be like a good choice to choose with your mechanical system.
Yep.
So you may, like, you're not going to get direct questions. It's going to be more about like a case scenario or a project in some location, and then how you are applying these concepts to your project as an architect.
And feel free, I mean, for psychometric chart specifically, there are so many videos on YouTube. I think I listened to maybe one or two people who are just to get an idea of it. But in general, I think YouTube is like the best help ever. I never thought of that until I was studying for my AREs. It's just and English is my second language, so sometimes I just don't even know a word. And when I YouTube it, I get a whole video of explaining that word, and it actually helps me much more. So not everybody might use it that way, but in general, like the word enthalpy, I don't think I ever saw it in any of the NCARB questions or anywhere, but I think it's one of those subjects that MEP actually gets really into it. And then it's just good to know, because when you look at psychometric chart, it's one of the main factors shown. The next chapter we're going to talk about is general refrigeration method, which is used on HVAC systems. And a very helpful YouTube video, it's Amber Book. I'm pretty sure everybody has heard about Amber Book. They're probably the best study guide for the area exams. Unfortunately, they're very expensive, but they the guy has a 40-minute of competence videos that he does. And if you email the Amber Book firm, just Google it, Amber Book, they'll add you to the email list, and they'll send you invitations every week with a Zoom link. But they also then post it on YouTube. So this one is free. It talks about HVAC terms. And this guy's so much knowledgeable. I don't know how he knows everything about every single building, but he explains it very well, which is kind of how I learned it at the end very well. Not very well, but like I'm presenting it. So in case you missed anything or I'm not explaining it well, I think this video will help everybody.
Hi there. Since
Yeah, you listen.
Going back to the
Psychometric. Sorry, your voice is very low. Can you speak a little bit louder?
Oh, psychometric. Is that very low? My voice is very low. So
now it's good.
Are we going to discuss anything? We discussed about enthalpy. Are we supposed to discuss something about sensible heat or latent heat, relative humidity?
I have not seen any questions about that specifically. Just because it's one of the main lines in the psychometric chart, I looked it up in the MEP book, but I honestly have not seen it anywhere in the NCARB sample questions specifically.
Okay, thank you.
Okay, back to refrigeration methods. So refrigeration system, anybody wants to jump in and just talk about it, or just say any different types, methods of like how a refrigeration cycle works or what actually happens in it? Like there are three main methods, basic types. Anybody wants to? We actually talked about a little bit about one of them.
Evaporation.
Evaporative?
Yep. Other two?
Conventional.
Compression?
Yep. Compression.
Convention?
Actually, I keep missing compression and convention, but compression, yes.
Absorption.
And then the last one is absorption. So we're going to talk a little bit about all of them and then how they kind of get into the HVAC systems. But it's just good to know that these are the three main refrigeration cycles. And now principles of refrigeration and refrigeration cycles. So this chart, I think it's really important. I've seen it in NCARB sample questions where you're asked for like which item is a compressor or which item is a condenser. So basically what's happening is there's like two different pipes. One of them, it's like there's a little bit of liquid into it, and then through a compressor in this portion, a gas is turning into a liquid. Like there's like high pressure, the gas is getting pressured, and this is all like physics, and I I don't think we're going to be asked about specific physics questions, but just if we go back to our elementary knowledge about physics, when you pressure a gas into a pipe, it turns into a liquid, and then when there's an expansion valve, that liquid, so you're not releasing that liquid, but then the liquid, because it has lower pressure, it's gonna evaporate and turn into gas. So basically this whole thing, it's the refrigeration cycle. And what happens on this side, because there's low pressure, when this transition between liquid to gas is happening, the surrounding area, it's going to feel cold. And I think in another, I don't remember this one, if it was in one of the other Amber videos, but I think the way, the example he gives, which is really good, it's when you, have you ever cleaned your computer with that spraying thing? And so when you actually use that spray, the can really gets cold. And so that's basically the low pressure portion of that refrigeration cycle. And obviously the other side, when it gets compressed, it gets hot. So we basically have to accept this as how it is. And then this whole thing is going to be used as a process. So sometimes in a building, this actually, it's far away. This whole process is going to be through pipes going into the building. The whole condenser section is outside. Sometimes it's in the mechanical room. And so the way we have different types of HVAC system, it depends on if you're passing this cold air through a cold water through the system, and then you transition it to air, or it's happening through just air through ductwork. So all those different designs turns it into this different HVAC systems that are there. And then when for any of these transitions we use, which is not in this main cycle shown, but whenever you use a specific chemical or basically, I'm sorry, that's my dog, for a salt solution, that's when absorption happens. So if you have a diagram that it's showing a salt solution, that means the chemical process of absorption is happening to help that refrigeration process. So anybody can think about, sorry.
So just to kind of make it easier, if you boil anything, if you boil like water, that's when you get steam, right? So that's changing the liquid into gas. Usually liquid will absorb heat to be changed into gas. And that's the whole idea here. It's the change, the liquid to gas change is absorbing heat. So it's providing the cooling. The other way around is giving.
Sorry, I don't know who that was. Okay. Okay, so think of this whole thing as a cooling system. Anybody can think like how this whole thing is going to be condensed in a system? Anybody can just think of a place that this whole thing is a combined version, like what would we call it in, and it's probably, just to give you a hint, it's going to be used in like old motels that you would go.
Swamp cooler?
Yeah, just like, yeah, I think so. That's another name of it. But yeah, just like a window system. So that's basically what it is, where when you walk outside of it, you're going to feel that heat because it's taking that, like that's releasing heat from the outside, but then it's just going to cool the interior side. So basically that would be just a tiny, every process of this refrigeration cycle happens in just one unit. Before I start about cooling tower, I want to ask if anybody knows what a cooling tower is and what does it do?
These are the giant tanks.
Mm-hmm. But does it
Well,
actually, what is it for, let's say?
You dump water in the top, it evaporates as it goes down, and somehow it makes things cold.
Yes.
Maybe
so,
the water's cold. I think the water's cold at the bottom because a lot of it's evaporated, and so then you use that chilled water.
okay, so that's good. Exactly. But the thing that we don't want to mix up is that the cooling tower is to cool this condenser piece. It's not to cool and make the air inside cool. That's something, if you think about cooling tower, we always think of, oh, that's the AC, or we think of it as the cooling mechanism of the building, but that's not the case. You use a cooling tower because the condenser portion gets really hot, that you don't want that whole hot air in like big buildings to happen. You use a cooling tower to cool that a little bit to cool that hot air that releases by the condenser. You cool it off sometimes, and it's different versions. This is just one diagram I grabbed from Google. Sometimes you just drop water on top of it. Sometimes there's a fan on top. So there are different systems, and I don't think we need to get super detailed about it. But I think we have to just know the cooling tower is to cool the condenser, and there's nothing to do with the air handling unit portion or the evaporation portion. That's something, the name really confuses me, and every time I look at a diagram that's showing a cooling tower, it feels like, oh, okay, so this is the cooling system, and then the boiler is the heating system. And so we have to know that's not the case. So this is another diagram to show how the cooling tower is related to the condenser, of thinking about that, how the fan, as whoever, I don't know who it was, I think it was Robin maybe, who explained it, and Rand a little bit. So how that actually cools the heat from the condenser, and then the air handling unit, it's actually cooling the inside of the building through that whole refrigeration process. So these are just diagrams I literally grabbed from Google. I think it's really good to look into different diagrams and just try to understand, again, not so much in detail, but get your eyes, I don't know, familiar with different diagrams, because a lot of them are saying the same thing, but it just looks different, or they're on two different sides. And easily in the exam, we might see a vice versa of it and just choose the wrong answer, because NCARB is the master of trying to confuse us. So just, I think, looking at different diagrams would be very helpful in general. And then this is, again, another version of the concept of cooling tower, how those fans is just going to cool the air and then get the cold. And this is not really a cold water, I want to say, but it's colder than whatever it's coming into the cooling tower.
I think it can get pretty cold, actually. This is Robin again. I think it can be pretty
Really?
cold,
Okay.
even in cold weather, I think.
Okay. Maybe, yeah, because I think actually you're right. Maybe, I don't know. Okay, that's good to know. So that's something I always thought, because it's just getting cycled back to the condenser. It might not be super cold. That's what my understanding was, but sure. I'm gonna look more into it. Thanks for that. So, and then here it's just another diagram I really like, because it makes me understand that the condenser, it's kind of here, and then this is the evaporator, and all the AHUs are here. So that whole refrigeration cycle, it's now divided up through the building. So it's not always as nice and neat as shown on the main refrigeration cycle. So just understanding how why would we need ducts and pipe work and all that to get water or cold air through different units. Okay.
AHU stands for air handling units.
Sorry, what?
The AHU, just
oh yeah, air handling units.
Air handling units.
Anybody can give me a quote, like a general, how different HVAC systems are, like what are the main divisions, general types of the HVAC systems?
I think VAV and CAV.
Sorry, what?
VAV, variable air volume, then constant air volume.
So yeah, those are both all air systems, but that's good. That's a very good start. Any other types anybody can think of?
Radiator?
Radiator.
More like a vertical versus a horizontal?
Yeah, maybe that would be divisions of heat pump.
Like an FAU?
But I think the general, like the big, if you look at a big picture, and then this is coming from Architect Studio Companion. So the rest of these slides are coming from Architect Studio Companion. That's a very good book. That one I definitely would recommend it. But again, it's really good to understand the concepts because different books, I don't know, Heating Cooling Tower, MEEP, and Architect Studio Companion, they have different divisions of these. They have it, and they don't necessarily match, but it's good to know how each of them it's good and whatnot, because what NCARB does is they give you scenarios and then you have to choose your outcome. So it's good to know which item it's the advantages and what are disadvantages and where would you use which of them. So in big picture, the systems are divided into all air, air water, and all water, and just local systems. And the main division is that these three are central systems, and then there's a local system. And local system is like the one we saw at like a window unit. And what we have to know about local systems in general is that basically are easily installed. Obviously, installation cost is pretty low. So lower operation cost, because when you think of that, it's like you are in a room and then if you're not using it, you can just turn it off. So there's much less operation cost. There is no ductwork or piping needed. As you're designing the system, you just need a opening through a wall to have that. And then obviously that's much less installation cost because you're not installing any of the ductwork and stuff. But there's much higher maintenance cost because it's usually gets damaged or something is wrong and maintenance is required. Maintenance actually happens in the occupant area, which is one of the main issues with the local systems, and it's noisy. So a lot of times we're going to be asked that noise is a really big concern about whatever system that we're choosing. So obviously we're not going to be choosing anything local. And our options are going to be in any of the central systems. And then the short lifespan of the equipment, and then we have a wintertime humidification is not really possible because this is just cooling the air, and then in the winter when there's dry, you cannot really control the quality of the air. So again, this is just something to know about central systems, and now we're going to get a little bit in depth about the all air system, air water, and all water systems. And so all air systems are mainly divided into, as I don't know your name, I said it right. You mentioned VAV and CAV, and that was great. Those are both types of all air, and that's because what all air system does, it's basically like when you get your air and you want to send it to your different rooms, it's going through an air and it's getting returned to an air. So that's like an all air system. Again, these diagrams are all from Architect Studio Companion. I mean, these black and whites, these guys are Google search. And I think I put all the, I believe is important things just for my record, and I'm just sharing it with you, the important portions of that book. So are kind of my note takings. So feel free to, again, read the book yourself and then share any comments you have with me. But these are just things that I thought it's important. So basically what happens in a VAV system, it's you have different temperature control in rooms because there is a damper in a room, and this one is a better diagram of what happens here in this box, is that when this central system, it's giving some certain amount of like heated air, for example, when it's heating, or cool air when it's cooling, by the amount or the angle of this damper, you are controlling how much of that heat or cold is coming through your space. So you have enough control, but the negative part is that you cannot cool this space and then heat this other space. So if the whole building has one VAV system, that's what you get for the rest of the building. You cannot just like it's not good for some certain buildings where you have for example, a data center that you always have to keep it cool. And then like it's this office area, which one floor has all these data rooms with wirings and always needs to be cold, but then the rest of the office, it's winter and they need heat. This VAV system, it's not really feasible because you cannot do two different systems on both times. And one thing to know about general HVAC systems, as Amber Book explains it, which is, I think it's really good example, it's like sometimes your building needs a mixture of them. It's not that always a solid answer, but it's just we have to, for NCAR purposes, we always have to know what are the negatives, what are the positives, and then according to that scenario they give us, we have to make a decision. I think Amber explains it as it's like a meal course, and sometimes the mixture of having a specific appetizer or a specific, I don't know, main dish or a specific dessert, that combination does not have a name. It's just you're having a salad as an appetizer, you're having a steak as a food, a cheesecake as a dessert, and then if that changes, it's still all a meal. So just knowing that sometimes there's a combination of two different systems that make a whole HVAC system of a building. And so in general, obviously a high degree of temperature, as we mentioned, it's a moderate cost and it's economical to operate. The negative part with it is that limited range of heating cooling, as we mentioned, and then if there's a different demand, as we talked, there's a secondary system that's needed. I think this one is really important. Alternatively, in buildings of moderate size, a package system may be used in place of all components other than ducts, HVAC terminals, diffusers, and grillers. A single package system incorporating all central components in a single metal box may be installed on the roof or outside an exterior wall, or a split package system may be installed with a compressor and condensing unit in an outdoor box, and an evaporative and a handling unit in an indoor. Multiple package systems are often used to serve buildings that are large and horizontal extents. For more detailed information, and this is again from Architect Studio Companion, so feel free to look at that. It's like the not so much of a thick book, but it's really good. And we're going to talk about split packages, systems, and all that eventually. And again, this book divides the VAV system in general up into different concepts, into different systems. For one, there's a reheat system, induction system, and I put here YouTube videos that you can later look into it. It's just, it helped me understand which one is which. So reheat, it's basically, there's another box in there that mixes that whatever happens here. So basically there's a reheat system here. And obviously it's not going to be really efficient because you're reheating that system again. Like if sometimes there's the cool air coming into, like you're cooling the air in this main room to come here, but then you need a hotter temperature in this room versus this, and then you're reheating it again. So that's sometimes not so efficient. An induction system, it's sometimes where it actually kind of grabs the air in an office area and then mixes it with the new air quality that's coming from the HVAC system, and then mixes them to release it. And that's sometimes a lot used in the office areas because like when the ductwork or the diffuser, it's right above one specific desk, you don't want that desk right underneath it to feel super cold, and then the rest it's just, so in order for make it that comfortable for the person or the other desk that are literally below the diffuser, you kind of mix the air that's already in that space and then mixing it back into the system. So that's like the induction. Fan powered system blends the secondary room, not just the room itself in the AHU. But uses a fan instead of an induction system, as explained in the induction VAV. The common application is additional cooling or heating in the building perimeter zone, so usually not used by itself. A dual duct system, that one it's probably very good because you have one duct for the cool air and one duct for the hot air, and then you mix it according to what you want. But the problem is it has obviously excellent local temperature control. Anybody wants to share what is the negative part of this? What do you think? There you have a big, like 2 different ducts.
No one's got room for all that.
Exactly. It's expensive. It's very space consuming. And obviously not energy efficient as we described in the reheat, because it kind of has that as you're releasing cold in one, hot in one, and then you're reheating it again somewhere else. But yeah, the main issue would be space. And then there's underfloor and air-to-air energy recovery. These are just general, I think, divisions that ACS explains. And it's actually this both, so they're the same that happens in the CAV system as well. This one is just going from the underfloor rather than putting the system in the ceiling. And new discoveries, I think I'm hearing it a lot, is that it's really good because when you are actually, if it's cooling the floor, thinking of it that way, when you're walking on it, you're gonna feel the cold. Like if it's summer and you need cold, you probably can keep it less temperature because your feet is already getting cold and your whole body will get that feeling of the cold, rather than making it cold from the top. And you have to, it takes time until it comes down and you feel that. So when your body feels it from the bottom, it's probably more energy efficient in general. And then air-to-air energy recovery, it's just that the heat energy in the exhaust air stream of the AHU basically returns back to the supply air. So you're using that heat already. So it's more efficient. Next, again, this one is also a CAV system. It's a, all air system. Basically it's again the same. It's just that it's literally constant. So what happens is that all of these are constantly getting the same air. That's this guy making. So the main difference, it's with VAV, if we just look at them side by side, is that it doesn't, this constant air volume doesn't have that damper thing on the VAV system in each of the zones. So it's just constantly pushing the air in. And that's what's happening in a CAV. Obviously it's good for large open areas. It's good for theaters, auditoriums, gymnasiums, exhibit halls, just because it's just one space that you have to, I guess, heat or cool. And so obviously the air quality, it's pretty controllable because it's the same. It's easy to maintain if there's just one mechanical area and anything happens there, and it's not, maintenance doesn't happen in occupied space. So that's one of the main things. And then the only issue is that it's single zone. It could be multi-zone, but then it's going to be called multi-zone system. A basic CAV system, it's literally just considered one zone. But if it turns into a multi-zone, usually it's more only like up to 2 or 3 zones. It cannot go all the way up to 10 zones or something. Then probably another system will be used if there are 10 different zones needed. And so those are the varieties that we talked about. So furnaces, it's like usually when you have a furnace that heats that constant, it's just used in single family homes. And then multi-zone is one of the varieties or versions of a CAV system. Anybody, we talked about some of the possibilities, but any other main for a multi-zone system? Anybody wants to guess? Or a CAV multi-zone? One of the main places that's going to be used is going to be museums, because you might need different temperatures in different exhibits, or in office portion of the museum, or classroom educational portion of the museum versus the main exhibit halls. So that's where you're going to use multi-zone and just have the exhibit halls in one zone, and then the office maybe portions in another zone. And then these two again are pretty similar. almost identical to the VAV system. It's just that it's a constant air and doesn't have that damper thing in it. And here's the diagram of the multi-zone system. So what happens is the fan room is the same. It's just they get divided into 2 different zones through that diagram, through that, mechanical room or fan room. And then only each of them goes to different zones. So you have more control of how much air. So here you have those dampers basically. And sorry, this is not really good copy, but if you have that book, I think if you even Google multi-zone systems, you're going to get pretty good diagrams. Okay, so anybody can tell me these two. One of them is a CAV, one of them is a VAV. So as we described, what's the difference? And I mean, probably it's hard to see. So the main differences are here. Let me mention that. Which one is a CAV? Which one is a VAV?
First one is a CAV, second one is a VAV.
You said this one is a CAV, this one is a VAV?
Yes.
Okay. And you were right. Because the only main difference between CAV and VAV is the fan supply, like how much fan energy you need. So that's really important to know. CAV obviously considerably has more fan energy or needs more fan energy than VAV. So other than that, they're pretty similar systems. Okay, any questions about all air systems?
Where does VRF fall in on that?
What is a VRF?
Well, it's like a VRV, right? But it's modified.
Sorry, I don't know those terms. Do you know what they stand for?
No, not off the top of my head.
Honestly, I've not come across those terms of the VRF. Anybody else knows what a VRF is?
That's more electronics.
I think it's a variable return fan.
Sorry, it's variable what?
Return fan, something like
Yeah,
that.
refrigerant flow. It's a.
Oh yeah.
So
Oh.
instead of having ducts, you use your coolant to bring over cold water and return the hot water out. So you don't really need a duct.
Okay, so I have not heard those terms, but those will probably be under water systems, either all water systems or air water system, if you're using pipes instead of, but I honestly, that was the first time I've heard about those.
Aren't those used for large refrigeration units?
I mean, they could be used for a small building.
They can be used on big buildings now because they are cost efficient for front cost. But once they start, renting out properties, that's when they need to buy their own equipment.
Sorry, again, can you say what was the acronym for it? FRV?
No, VRF.
VRF, okay.
Yeah, variable refrigerant flow. So instead of having ducts penetrating your buildings, you may use your pipelines.
You're running pipes of gas around instead of ducts.
Oh, not gas, actually.
Oh, I'm sorry. Yeah, not gas. Of refrigerant. Of refrigerant.
That's right, refrigerant.
Actually, we have that somewhere in one of these talking about like split systems that actually have refrigerants running through them. But in the NCARB world, I guess, I don't know, it's called like mini SWIP system rather than, I've never heard the variable refrigerant flow, but it's good to know different names of it. But yeah, that's exactly what happens when you run the, I guess, refrigerants through the pipe.
They also have another system that's the high pressure to aspirated, which is the same thing. It's a HVAC, but it's just highly pressurized air and very small ducts. And then all the duct ends are all lead dampeners to dampen the noise, but it's coming out at a high pressure. So that way you can
Wouldn't it fall under the VAV if it's getting the cold or hot air through the ductwork?
It is, yeah, it does fall under one of those, but it's just doesn't, the fan unit is like a compressor, you know, it's a really high pressure, so it comes out at a much higher, so you can run smaller ductwork, but all the ductwork has to be able to withstand the high pressure.
But, and you're saying for noise, because if it's high pressure, I'm just thinking it's going to cause a lot of like noise through the pipe, through the ducts. And
So and then the ducts all have an insulation, a sound insulation around them.
Okay.
And at the registers, they're a heavy metal, so it dampens that.
Cool.
But they just, anyways, it's Unico is one company that makes it.
Unico. Okay.
Yeah.
Good to know. Cool. So yeah, as you can see, there are all different names and versions of this whole thing. Okay, so next is air water or water to air system. Architect Studio Companion basically combines it all into air water system. But when I was looking at Amber videos, they talk about different, it's air to water or water to air might be different. And I don't think we really need, as for AREs, to get into bits and pieces of this, but the difference mainly between the air to water and water to air is basically which portion is happening in the condenser through the evaporator. So when it's air to water, it means the high pressure portion or the hot version, the hot piece, it's actually air on the condenser side. And then the water, for example, if there's pipes through the building that passes the cold to the building, it's a water, versus if the high pressure, it's water, and then it actually gets the cold or hot air through the fan. So that's basically the main general difference of water to air or air to water system. And one of the main air water systems, it's actually active chill beams. And active chill beams, it's, anybody wants to know, anybody wants to chime in, where would it mainly be used?
Well, aren't they more effective for cooling than they are for heating?
Yes, but they actually do both.
Go hospitals.
Hospitals and lab works, actually laboratories. I've seen laboratories in lots of sample questions, but I think hospitals are good ones too. And so it reduces the chance of transporting air pollutants because it's just passing it through the pipe. Pipe water is closer to room temperature, so that's why it's renewable. It's more energy efficient. And then it changes, it's energy efficient, more energy efficient compared to other systems like the heat pumps or geothermal, which we're going to get into eventually. And obviously there's no fans in the occupied space. So one of the other things that reduces maintenance costs, because maintenance only will happen in the main room and not in the occupied area. And this is basically what it does. It just, the beams are cold. So it basically, when the hot air rises up, it gets cold and then returns back. That's mainly the air water system. Anybody that has more information on them you guys want to share on air water or other types? I thought I had more on that. But...
So I just added a YouTube video for explaining VRF. It's like 15 minutes of deep explanation of what's the VRF system, and I added another video of more of like a 2 minutes more of a general explanation of the VRF system. So just
yeah.
Where do we look it up on YouTube?
It's in the chat. I just added to the chat. Just click the link in the chat and you'll be able to see
Great.
it.
Chat, but I also added to the slide. We're gonna pass this, yeah.
It's a good system to know about in case you get a question or you want to know about it in real life. variable refrigerant flow. Yeah, we have it.
Okay, I'll just save this here so when we pass the slides, you guys can have that. Thank you, Mohammed.
Yep, thank you.
Okay, next would be all water systems. So all water systems is basically both sides, both in the condenser and evaporator side, it's coming through pipes. So obviously the very good thing is that you don't need room for ducts, so everything happens through the pipe. And it's efficient, where extracted heat from overhead areas can be used to heat the underheated areas. But it's actually expensive. Anybody knows what's the main issue with in general with all air systems? Oh, sorry, with all water systems.
You have indoor air quality issue because you don't have the fresh air.
Leakage.
Somebody else want to say something?
Leak.
Leaks could be issue. Condensation could be issue. Yeah.
Maintenance.
Mold.
Yes, but the main issue as far as air quality is humidity. Exactly. Humidity control, it's a big issue because you're not controlling the air that's coming in. So in general, again, I think just knowing that all the water system has humidity issue, leak issues, or pollutants, I think it's compared to the other two. Obviously, those two are not the best as well, but just knowing that the fan coil terminal systems has that. And then so there are two main types. It's the concealed fan coils and then dedicated outdoor air system. So they're just general types of the fan coil terminal. So that's probably the outdoor air system. It's more better air quality, but in general, they're expensive systems. The closed loop heat pump system, it's a little bit more economical, but it's just for heating. So good thing to know, just to know, it's like the heat pumps are just for heating and not for cooling. So for humidity control and for cooling, other means or other systems needs to be implemented into the heat pump. And then another one is the fin tube convector. And then this one, actually, it's the one we talked about a little bit, like a kind of a mixture with sometimes VAB where it's in the bottom, but this one is like all water version of it. So it's greater occupant comfort and operates more efficiently than all air. Low maintenance costs, we discussed this, works well with renewable or efficient energy sources such as the heat pump, geothermal exchange, or solar hot water. So you can basically mix this, the convectors with the geothermal radiant heating, but obviously there's still a humidity issue. And that's, I guess, happens in general, condensation, humidity, that's issues that happen in general with all water systems. But again, these are just the important things, parts I took from Architect Studio Companion. Other important stuff to know in general is split system versus mini split system. And these could be, I guess, as part of air water systems. It's as, because I always thought the mini split, it's just a mini version of the split system, but that's not the case, apparently. A split system is going to be, because it's just one condensing, taking it to the AHU unit inside, it's just for small buildings, residential, and single families. But the mini split system, and I just put it here because I always mix this, probably some of you might already know, but it's just that it's much more efficient because you can use it in bigger buildings, and each of them can have their own cooling or heating. So one of them can do the cooling in one room and the other one can do heating in another room. So as it says, it's mini, but it's actually for bigger buildings. So that's something to note. the other important thing, it's a difference between a fan coil unit versus mini split system. They're actually both in their room. They both can heat or cool, and they both have a fan blowing across the coil. But the main difference is that in the mini split system, it's the refrigerant blinds that actually brings the cold from the condenser to the air inside. But in a fan coil system, it's actually chilled water. It's not this one is a chemical, but this one is not. So these are things to know. Other systems or diagrams to look into. Sometimes they actually, NCARB loves to give us low quality pictures just to understand how this one, anybody wants to chime in of what these systems are? These yellow boxes. I mean, basically, what's the difference between this and this?
The left is your split system.
Mm-hmm. Yep, this one is the furnace versus AC. So the heating and cooling, it's actually separate. They're kind of, yeah, as mentioned, they're separate. And this one is like a package system and could be used for like a little bit bigger buildings. The other thing too, this one, it's actually really important. I've seen a lot of questions on him. This is this lady, I don't know her, I mean, it's a she who has records these videos, designer masterclass. They're really good videos. They're like 2 to 3 minute videos. I just sometimes put them on repeat when I'm cooking or whatever. Just has a good summary of everything, and then they actually provide a free cheat sheet. This video, YouTube video is actually specifically for geothermal, but just go through their channel. I think the information they provide is really good. And this one talks actually about different geothermal systems. And this is something pretty important to know. Geothermal systems are getting pretty popular, but there are different versions of them. There's horizontal, vertical, pond, which are all closed, and there's also an open loop system. So technically there's 4 in total. Vertical, it's actually when it's more in an urban setting and you don't have enough land space to do it. So you have to go all the way deep. And that what happens in geothermal system basically is you're using the heat or cold of the earth to cool or heat your building. Because either it's winter or whenever, 20 feet underground usually has the same temperature all around the year. It doesn't matter what region you are. So usually if it's summer, below the earth, it's colder and vice versa. So you're using that cold to actually cool down your building, or you using that heat to actually heat your building. Mm-hmm. But things to consider is that horizontal versus vertical. Horizontal is obviously much cheaper because you don't have to go all the way that deep, but the issue is that you have to have enough land around yourself, around the building, and in order to be able to actually build a horizontal geothermal system. A pond or lake, it's actually using the heat of the water or the pond around it, but obviously if you have a scenario that there is no pond around it, this obviously it's not a choice. And then this one, for the open loop, you are actually not using the pond water, you're using the groundwater. And so if you have to know which level or how deep you have to go in order to get to a well or groundwater in order to be able to use open loop system, which is basically 2 different pipes that are returning. So we have 3 sample questions. Anybody has any questions, systems that we didn't cover you guys can think that I can add to the slides and pass on, or I don't know, anybody has ideas you guys want to share? Okay.
There is a system where it's geothermal, where it's just air traveling under, that you just intake of air and it travels under the ground and then it gets brought into the building with no, just using the ground to cool the air by transferred from below the ground. So it's not like,
is it considered any of these? So it's not a heat pump, but it's just a geothermal air system, basically?
that's what it is.
Okay,
Yeah.
I'll look into it and then I'll add that information.
I think geotech, you can do cool and you also can do heat. You utilize a geothermal system. You can cool the air, cool down for the summer, and you can use it heat during the winter.
Okay. Well, I'll look into it. I'll try to find information and add it to the slides before passing them on. There are 3 sample questions. 2 of them are actually from NCARB 4.0, and anybody taking the exams definitely go over NCARB 4.0 and 3.0 questions. For 3.0, don't get thrown off. There's like heavy structural calculations. I'm 90% sure we're not going to get any of those. But there are some questions that are going to exactly show up on the exam. So go over those questions. They're the NCARB questions. And I've had them on all of my exams that you get similar questions. So definitely take advantage of that. Okay, the system draws hot water from the boiler room and transfers it to the delivery unit that are usually a simple metal enclosure housing horizontal pipes with closely spaced vertical fins to circulate that hot water through the fins. It uses convection to deliver heat to the space, while delivery unit with an inlet at the bottom draws cool room air and circulates it through heated fins and discharges it through the room via outlets at the top. Which one is it? Closed loop heat pump, through the wall unit, VAV, or hydronic convection? We can actually look into the diagrams that we had.
Closed loop.
Closed loop, why? Can you?
Because you're circulating the air from the floor through the ceiling constantly.
But it draws hot water from the boiler room and transfers it to the delivery unit. So here are the highlights. It uses convection to deliver. It discharges it via outlet at the top. I think the main issue is the boiler room here. In a closed loop system, you're using the heat of the ground and you're not really boiling it up. So it's actually a hydronic convector. And these are, I put it here just to encourage you guys. LF Byram, her questions are really good. She actually, if you even passed your pro practice questions, she has actually a combined PA, PPD, PDD. So like it's discounted if you buy all 3 together. She has very good questions. She has very good explanations. To like, I can actually show you, let me find it, explanation of answers. One second. So yeah, I would really recommend her questions because she even brings up the pages. I cannot find it right now at this very moment, but I'll just show you another. Actually, here there's. So here she explains the whole thing. It's a hydronic convection according to, and he brings up like the actual, the reference of where she got the question from. And sometimes when we get a question wrong, it's really good to just go and read the whole chapter. So I'd highly recommend her, and I put the link here in case anybody else wants to purchase that. And this one is from NCARB. So here's a diagram. The diagram above schematically illustrates a typical chiller and cooling tower cycle. Which point is the compressor located?
A.
Why?
Because it's gone through all the systems and then it's forcing it back into the system.
Well, I guess it'd be.
Why would it be B?
Compressor, you should press the air into the liquid.
Mm-hmm. Yeah, it is B actually. So looking at the cooling tower here, and this is probably your area, your room or whatever. This is the cold air cycling back, but this is where actually this is expansion expansion valve, and then here's the compressor. So it's right in the middle where it's getting the transition of the hot air, and this is the cold air. So yeah, just looking into, again, different diagrams, just even like Googling and hitting the image just to see different versions, I think would be really helpful to get our eyes familiar with any other diagram. And then here's the last question. In this drawing, above of a refrigeration system for a large building, what is the term for E? Where's E here?
Cooling tower.
Yeah.
Exactly. Yep. It's the cooling tower. So, as we discussed, feel free to go over NCARB. I'll try to have more sessions for like electrical and other sections. But anybody else who also wants to volunteer, feel free to let Mohammed know. But let me know. I think Mohammed will share my email address in case you guys found an error on the slides. I'd appreciate it if you let me know. If you found good resources, let me know so we can pass it on to everybody. I know this is not an easy journey, so let's help each other out.
Yeah, so
Guys.
if anyone really has finished his exam or is studying in a subject where you feel you are really good at that subject, or you have some information that you can share. That's the whole idea of these sessions, really, for us to share information between us, and that's how everyone is learning. So yeah, just reach out to me if you feel you want to co-host a session. I want to thank you all for attending, and big thank you for Pardees to put this whole presentation together. That's a lot of information. Thank you so much, Pardees.
Of course.
Thank you. Yeah, and yeah, just reach out either to Pardees if you feel anything, if you have more information maybe to add, or reach out to me at any time. Thank you all, and good luck with your exams.
Thank you. Thank you so much.
Yeah, have a good night.
All right. Take care.
Bye-bye.